Hello everyone, welcome back to these videos on light matter interaction. In this video we are going to continue with the Jaynes Cummings model that I wrote, the Hamiltonian that we derived in the last video here. And we said at the end of the last video that we were going to compute the eigenstates of this coupled light matter Hamiltonian, the Jaynes Cummings Hamiltonian. And we also discussed the matrix form that this Hamiltonian has. In particular, the Jaynes Cummings Hamiltonian is block diagonal in blocks that are 2 by 2. The reason for this is that if we fix the number of photons in the cavity, if we fix the parameter n, the number of photons, then the only possible coupling between eigenstates of the unperturbed system are between the excited state of the atom with n photons in the cavity and the ground state of the atom with n plus 1 photons in the cavity. One comment that I want to do here is that if we define the total number of excitations operator nt, this is the number of photons in the cavity plus the atomic excitation number, then you can compute the commutator and convince yourself that the commutator with the Jaynes Cummings Hamiltonian is equal to 0, which means that the total number of excitations in the system is a conserved quantity. And this is a feature of the Jaynes Cummings Hamiltonian. If we didn't do the rotating wave approximation, so we don't actually arrive to the Jaynes Cummings Hamiltonian, we arrive to something more complicated, then this quantity is actually not conserved. So this is a feature of this Hamiltonian, and is this symmetry in the system that allows us to actually diagonalize the system analytically. So in order to diagonalize the system, the Jaynes Cummings Hamiltonian, to find the eigenvalues, so the energies of the coupled light matter system, the atom plus the light, and also the eigenstates, we just have to diagonalize one of these 2 by 2 matrix with the parameter n unspecified, let's say, just for any n, and then we diagonalize all of the blocks. Given the n, I can tell you what are the diagonal forms. So the only thing we have to do in order to diagonalize the n is project the Hamiltonian into this subspace. In other words, what we can do is to compute, well, I wrote it here, sorry, to compute the elements of the Jaynes Cummings Hamiltonian of one of the subblocks. So this means we have to compute elements of this type. These are the 2 diagonal elements, G n plus 1, Jaynes Cummings G n plus 1. These are the 2 elements that are diagonal in this subspace, because the subspace is the subspace of these 2 states, right? Okay. So in this case, for example, you see in these both cases that the contribution of this term, of the interaction term, is 0, because the interaction term is going to create or destroy excitations in the system. So this means that then when we do the bracket, they are orthogonal to the state that is on the left, so they are going to give 0. So the only contributions for the diagonal terms are the first 2. So for example, in the first one, the excited state will give h bar omega naught from the first term, that is the atomic term. And then for light, we have n photons in the cavity, so h bar omega n. And the second one, very similarly, the energy of the ground state is 0, so it's 0, the first term, and then the second term is h bar omega n plus 1. And the only one that we have to compute, apart from these 2, is the off-diagonal term, which is this. Now, the first 2 terms are going to actually give 0 for the off-diagonal terms, because they are diagonal, so they will give something times En, and then En is orthogonal to Gn plus 1, so it gives 0, and it's the second term that will not give 0. If you see the last term of all, this term, sigma dagger A, is also gives 0, because sigma dagger applied to the excited state gives 0, because you cannot raise more. There are no other level than the excited state in our model, so this will give 0. And then the term that actually will give you something is this sigma A dagger, so is h bar G, and now G n plus 1, and now this sigma A dagger. Now sigma applied to the excited state is the ground state, and A dagger, so A dagger applied to a stem m gives square root m plus 1 applied to the stem m plus 1. So it will give the state m plus 1, but then we recover a square root, and the square root in particular, it was applied to n, so it gives m plus 1. And so in other terms, if we just write the matrix form of the Hamiltonian, we just write the matrix with these elements. This is the Jaynes Cummings Hamiltonian, but a 2 by 2 block. It just gives h bar, and then here we have omega m plus 1, then g square root m plus 1, here the same because g is real, and then here I have omega 0 plus omega n. This is exactly what we just found. I'm just rewriting it. And now we have to diagonalize this 2 by 2 matrix. This is a bunch of algebra. So I was thinking if doing the calculation for the video or not. In the end I came to the conclusion that it's not very worth it to do it. It's nice if you want to do it at least once, because you see how terms collapses and the expression, the final expression is rather simple compared to the equations you have to solve. But the idea here, if you want to do it yourself, is to diagonalize this Hamiltonian, which means that you would do this matrix minus lambda, the eigenvalue matrix, times the identity in 2 by 2 identity. This is 0, so this gives an equation of second order degree polynomial for lambda, and then you find the two solutions. And I'm gonna just write here the solutions that we find, which are lambda plus and minus. They are defined like this, but these are energies in the end. These are omega times m plus 1/2 plus omega 0 divided by 2, and then plus minus for the two solutions square root delta square plus capital omega n square. This delta is the tuning, we discussed it many times, omega minus omega 0, and this omega n is the one photon Rabi frequency that we also defined. It's just, well, it's almost the one photon Rabi frequency. It's just 2g square root m plus 1. Okay, so these are the eigenenergies of the system that we will discuss at the end when we see the spectrum explicitly. But now let's compute the eigenstate of the system. Okay, and for the eigenstates, which is what we were looking for in this part of the video, well, we applied the Hamiltonian. So the Hamiltonian is with an h bar here. Also this omega, these lambdas here, these eigenvalues, they have the units of frequency, because I just diagonalize without the h bar, but don't worry about it. In the end, if we need energy, we multiply by h bar. So actually, let's not put the h bar because it's trivial. So for calculating the eigenstates, what we do now is we say, okay, we have the Hamiltonian that I'm gonna rewrite g square root, well, yes, sorry, I'm gonna, just to be faster in the end, I'm not fast, omega n divided by 2, and then omega 0 plus omega times n. So this is the Hamiltonian without the h bar. Then this applied to a eigenvector with components a and b. This should give me these eigenfrequencies, which are all these things, applied to the same eigenvector. And now if I take the plus solution, I will have two equations that are redundant between them, and if I got the minus solution, I will also have two equations. These two equations are two equations for the coefficients a and b, but they are actually the same equation because it's an eigenvalue problem. So this means that this gives me the relationship a as a function of b, and vice versa, of course. and the same here. And then we apply the normalization condition. Since a and b can be real here because all the numbers in this matrix are real, then a squared plus b squared is equal to 1. So with all of this, we find the solutions for a and b, and so the eigenvectors. So I'm going to just do 1, and if we just do 1, we get the following. So just applying the plus solution and taking the first equation, one finds that a is equal to 2 divided by omega n, and then one has omega minus omega 0 divided by 2 plus the square root of delta square plus omega n square divided by 2 times b. So this is the relationship between a and b. And now this is the detuning delta, and this 2 goes away, so we just find that delta plus the square root of all of that divided by omega n b, this is a. And now what we do in order to solve this problem is a 2 by 2 matrix. So when we are trying to diagonalize a 2 by 2 matrix, and we know that a diagonalization of a 2 by 2 matrix that is for eigenvectors that are normalized in the end is a rotation in the space, is a rotation in the plane x and y defined by this a and b axis, let's say. So we know that there is going to be an angle of rotation, so this is screaming to you that you should complete a triangle, and in particular we can complete the triangle given by C. So this is the angle that I'm defining. So if this, for example, if this is the detuning and this is capital omega n, then this is exactly the square root of delta squared plus omega n squared is the hypotenuse. So this gives me the relationships that the sine of this angle phi is equal to delta divided by the square root. The cosine of the angle is the other, is omega n divided by the square root, and the tangent of the angle is equal to delta divided by omega n. But then using exactly this equation, so these relationships, this equation is that a is equal to delta divided by omega n is the tangent, so this is the tangent of phi, plus the square root divided by omega n, which is 1 over the cosine, or also called the secant, but 1 over the cosine of phi b. And now the tangent is sine divided by the cosine, so this is equal to sine divided by cosine, so sine of phi plus 1 divided by the cosine of phi b. So now what we will use is the opposite actually, but just this is a matter of convenience. We will use that b is equal to the cosine of c divided by the sine of phi plus 1 times a. It's just the opposite. And now what we use is that b squared plus a squared is equal to 1, so this means that b squared plus b squared is all of this square, so this is cosine square of phi divided by sine phi plus 1 squared times a squared plus a squared, because this is b squared plus a squared is equal to 1, but this is a squared that multiplies, and now 1, but 1 is sine of phi plus 1 squared divided by the same, but you know where we are going here, plus the cosine of phi, which is actually the first term, all divided by sine of c plus 1 squared. Okay, now we can develop this square. So this is sine squared plus twice sine of c phi plus 1, and now this sine squared with this cosine squared gives me 1, and then plus 1 it will give me 2, so in the end I have a squared that multiplies. Now this is 2 times the sine of phi, which is this term, plus 1, which multiplied by 2 gives me this sine squared plus cosine squared plus 1, and then divided by sine phi plus 1 squared. But as you can see, these go with the square, so it reduces very nicely to a squared that multiplies 2 divided by the sine of phi plus 1. So this means that a is equal to the square root of sine phi plus 1 divided by 2. But this is exactly, if we take the half angle formula, this is exactly, and let me check if it is the sine or the cosine, because I don't remember right now. This is exactly, yes, this is exactly the cosine of phi divided by 2, if I remember well. Maybe it's the sine. The thing is that it's the sine of some half angle. So this is nice because then, well, we find if this is the cosine, then b is the sine. I'm not sure if it is the cosine, but you got the gist of how to solve the problem, which is the main reason. And this is correct until here. This is the sine. And so we find the eigenvalue, but they are very simple, in a very simple way. In particular, I'm gonna just write the solution to our eigenvalue problem was that the energies that I call lambda, but I'm gonna call now the energies, given the number of focus states n of the coupled system is h bar omega times n plus 1/2 plus h bar omega 0 or omega naught divided by 2 plus and minus the square root of delta square plus 4g square. I'm writing explicitly this capital omega square n plus 1, and then the eigenvalues that we denote plus n and minus n, they can be defined, actually, if you do the math a little bit more proper than what I did here, as these eigenvalues, or these eigenstates: gn plus 1 minus the sine of this angle en, and then the other eigenvector, sorry, or eigenstate is, we denoted as minus n, is the sine of theta n g n plus 1 plus the cosine of theta n en, and this is the main result of this section, because these are the dress states, and these are the energies associated with these dressed states. They are called dressed states because, as you can see, the eigenstates of the coupled system are quantum superpositions of eigenstates of the unperturbed system. So there's the interaction between light and matter is mixing, is entangling, is creating actually quantum correlations and entanglement, because it's a quantum superposition between light and matter, so that light and matter is not defined in reality, this is quantum mechanics, by itself, but is defined as a complex. It's not light or not matter, it's a combination of the two. So one says typically in the jargon that the atom is dressed by the light, and vice versa. You can also say that light is dressed by the atom. And that's why we have this plus n and minus n eigenstates. Now, one thing I want to point out is that even though we denote it with n, the plus n state doesn't have n photons in the cavity. For example, the plus 0 state, if we just apply this, is the cosine and the sine, but then the states that are mixing are g1 minus the sine, and then it will be E0. So yes, there is a certain probability given by this square of the sine of theta n that there are 0 cavities in the 0 photons in the cavity, so the cavity is empty. But there is also the possibility that the cavity has 1 photon. So is this number, the number state is not a good quantum number, if you want. So this number, it just tells you what is the state, it's a label, but it doesn't mean that the cavity is empty. If it is 0, for example, that the cavity has 2 photons, if it is 2, it is not true. It's a quantum superposition between n and n plus 1 states on the cavity. Okay, another thing for the matter of defining well the things is that this theta n is 1/2 the arctangent of 2g square root n plus 1, which is this capital omega n divided by delta. Okay, so let's see 2 things. First of all, let's do a sanity check very quickly, and this type of sanity checks are a good practice in this type of calculations. That is, what happens to the energies if g is equal to 0. So if there is no light matter coupling, what are the energies? So one gets E plus is equal to, is gonna be h bar omega n plus 1/2 plus h bar omega 0 divided by 2 plus, and now the square root, if g is equal to 0, all this second term in the square root is 0, so one only has delta squared. With the square root it goes away, one gets delta. And here, by the way, I'm missing a 1/2. This is 1/2 this square root, sorry. So we have delta divided by 2, but delta divided by 2 is omega minus omega 0 divided by 2, omega minus omega 0, or both of them divided by 2. And of course, h bar, I'm also missing an h bar, sorry for the double error. Okay. Alright, so now what we have is the following: h bar omega divided by 2 plus h bar omega divided by 2 from here gives you an h bar omega. So this is h bar omega that multiplies n plus 1 extra h bar omega, and h bar omega 0 minus omega 0 goes away. And this is exactly the energy of the state g n plus 1, which makes sense, because in the case that g is equal to 0, the eigenstates are the same eigenstates as the unperturbed system, which are, we consider them to be g n plus 1 and E n. So this is the energy of this, which makes sense. And then the E minus, for the same reasoning, is gonna be h bar omega n plus 1/2 plus h bar omega 0 divided by 2. And now we change the sign of this, so h bar omega divided by 2 plus h bar omega naught divided by 2. But what is this? Well, h bar omega divided by 2 goes with this 1/2, so one has h bar omega n plus h bar omega 0 divided by 2 plus the same is h bar omega 0. And this is exactly the energy of the state, excited state, which is this energy, and n photons in the cavity, which is this energy. So it makes sense. It's a good sanity check. I like to do this type of things. Another thing that I want to see is what happens with this angle. So if delta, the tuning is 0, so omega is the same as omega naught, then we can see that the angle theta n goes to, so the arctangent of infinity, because it's something divided by 0, it will tend to pi over 2, and then we divide by 2, so it's pi over 4. And this means that the cosine and the sine of this angle gives the same contribution, 1 over square root 2. So then the plus minus states are basically equal quantum superpositions between the two states. 1 over square root 2 gn plus 1 minus en, and the other, the minus n, would be something very similar with a plus sign. And this means that they are maximally entangled. So, as one could already kind of expect, when the frequency of the field in the cavity coincides, is resonant with the frequency of the atomic transition, the states are maximally entangled between light and matter, which is reasonable. And now what happens if the detuning is large, goes to infinity, or if the coupling goes to 0, then this angle tends to 0, and then if the angle tends to 0, there is no entanglement, so the eigenstates will recover the unperturbed eigenstates, and we can see that there is no Rabi oscillation. So basically the two systems, they don't talk to each other because they are very, very, very far away one from the other if the detuning is large, or simply they don't coupled. So it also makes sense. And these are these two extremes. Alright, so these are the eigenstates. We will use these eigenstates in the future in order to compute and to create non-classical states of light, like for example Schrödinger cat states in the next video, Bell states, and this kind of nice states. But for the time being, right now, let's look at the spectra. So let's look at these eigenenergies to see what is happening when we turn on the interaction. So let me put the unperturbed system. So let's say, what is the spectrum of the Jaynes Cummings model that we just calculated, because the spectrum is a way of saying what are these eigenenergies. It's a function of n, but there is a nice visual way of seeing what is happening. So imagine that this here is the ground state and 0 photons. Then at some distance I will have the energy of the ground state again, and with 1 photon, and this difference in energy is omega. I will consider for this spectrum that omega is equal to omega naught, just for looking at what is happening. In that case it is simpler, but the features are the same if they are not equal. Not very far away, but not equal. Then I will have 2 photons in the cavity, and then 3 photons in the cavity. So these are eigenstates. These are omega. Then on the other side I will have the excited states, and now this is the excited state energy, but actually the excited state has some energy which is omega naught, but we are considering that it's the same as omega, so these two lines are at the same height. These two lines are at the same height, so they are the degenerate state if omega is equal to omega 0. And this is the state with 0 photons in the cavity, but the excited state. Then we will have 1 photon in the cavity and the excited state, that of course this is omega. And then we will have 2, etc., etc. And what happens when we turn on the interaction? So what we see, if we just plot the energies of the system, this E plus minus, is the following. Now the ground state of the system here was G0, right? But recall that in the Jaynes Cummings Hamiltonian the ground state is also G0, because the state G0 has 0 total excitations. So the number of total excitations is equal to 0. there is the atom is in the ground state and there is no photons in the cavity. So this state cannot couple to anything in the Jaynes Cummings Hamiltonian, because you need at least some energy in the system in order for both systems to start oscillating between them. But this state is perfectly valid, and this state is we can actually see it from the equations that we did before. This state exists and is the ground state of both the Jaynes Cummings and the unperturbed system. This actually is a little bit technical, but this is important in order when we open the system and we can consider losses and we have to solve master equations. The fact that the ground state of the Jaynes Cummings Hamiltonian is actually a separable state, because this state is separable, it doesn't have entanglement between the two. This actually helps to solve these master equations, but this we will see in the future when we open quantum systems and etc. But for now I want to say that because now this is also the ground state when the interaction is not zero. And now we will have the plus and minus solution, the first ones that will be here and here. This would be the minus 0 and the plus 0. Remember that even if we write 0, there is a probability of a photon to be in the cavity. So just to be very clear, the plus 0 is a quantum superposition between G1 and E0. So the cavity can be populated. You need some energy in order for both systems to start giving back and forth this energy in a coherent way. And now this splitting here, the splitting is going to be given by 2g square root n plus 1. So here n is 0, so this is 2g. And this 2g is called and this splitting in particular between these two states, plus 0 and minus 0, is called the vacuum Rabi splitting. And there are experiments in which you can measure this. You can measure this splitting when light enters into in the resonant regime with the atom, with a qubit in general. It could be a superconducting qubit, as we will see in the future as well. I'm talking about atoms because it's historically how we found out this field, but there are solid state platforms that have equivalent properties to this. Then we will have the other two states, which will be the minus 1 and the plus 1, and now this splitting between the two compared to the degenerate case that was before the perturbation is 2 square root 2g, and then etc. So as you can see, what is happening is that when we turn on the interaction, light and matter interact, it couples the system that starts to exchange energy between the atom and the light and entangles both of them, such that the new reality is that you don't have an atom well defined or light well defined, but you have both of them. And these are the new eigenstates of the system, which are quantum superpositions of eigenstates with a difference in 1 on the photon in the cavity and the ground unexcited state. And these are the dress states. And what was before the degenerate state, now it splits. And this splitting is very important for some effects in atomic physics, like for example photon blockade. And the interaction in itself is also very useful in order to create non-classical states of light due to the interaction with the atom. And we will exactly see that in the next video, in which we will use exactly this Hamiltonian and this interaction to create Bell states between atoms and to create Schrödinger cat states as states in the cavity that I will define, if you don't know them, in the next video. So keep tuned and see you there in the next video. Ciao ciao.